Well, hello physics folks, and welcome to Doc Onco Physics. Keith Onco here. Today what we want to do is we want to take a look at Newton's laws, and this is actually Newton's laws lesson part 2. In part 1 we kind of left off with the steps on how to analyze a system of objects using Newton's laws. So I'm just going to review those steps again, and then we're going to go on to talk about systems of objects, free body diagrams, and then actually do some solving of some problems using these rules that we're about to go over. So the steps to analyze a system of objects using Newton's laws. In a minute we're going to go over just what a system of objects is, all right? But the first thing we need to do anytime we're going to do any analysis using Newton's laws is we need to identify what all of the objects are in our system. In our system will be comprised of one object, maybe two objects, maybe sometimes three objects, but usually it's one or two objects. And our object, what determines whether something is an object in our system, is if that thing has mass. Okay? Sometimes we like to alter our system a little bit and make it a perfect system, and so we'll assume that some things have no mass. Like I may have a block connected by a lightweight rope to another block, and I'm really only interested in the blocks, right? In the mass of the blocks. I mean, this one might be 20 kilograms, and this one might be 40 kilograms, and you might hear something like the rope connecting them is lightweight. Okay, and what it means is that it's essentially massless, and we're not going to consider it to be part of our system. That's not to say that the rope isn't connecting the two blocks, because it is, but we consider it to be like a perfect rope. There's no stretch in it, there's no mass in it, and it is just conveying a force between one block and another block. Okay, so essentially an object is an object in our system if it has a mass. Okay, so that's the first thing we want to do. The second thing that we're going to do is we're going to label all the forces on each object. So if I have a system that's got more than one object, right, I'm going to identify each object and then draw in all of the forces on each object one at a time, one object at a time. All right, I treat the objects separately in our system, and that's a key in analyzing a system using Newton's laws. We only have to deal with one object at a time. Okay, we don't have to deal with the whole thing all at once, because that can become overwhelming. 3, if the forces are at an angle, we need to break them up into their x and y components, because we only deal with forces that are either in the x dimension or in the y dimension. We do not deal with forces that are at an angle, so we will have to break them up. Okay, so that's number 3. Number 4, we're then going to write a set of equations using Newton's second law for each object, and we're going to have one equation in each dimension if needed. All right? So if you have forces that are in the x direction and forces that are in the y dimension, we're going to need two sets of equations. Okay, and then finally number 5, we're going to solve the equations. Okay, these are the steps. If you follow these steps, analyzing a system using Newton's laws isn't too difficult. If you skip some of the steps, that's when we run into problems. So first, let's go into a little bit more about what a system of objects is. Okay, so I've drawn 3 different systems here. I've put pictures up of 3 different systems. Okay, this object, or the system on the left, right, has 2 objects that we're going to be concerned with. This one over here that has a weight, and the car over here that has a mass. Okay, generally in a general physics course, we consider our cable here, or our rope, whatever it might be, to be massless, and so we don't need to be concerned about it finding forces that are acting on that rope or on that cable. There will be a tension or a force in the cable that is passed along and through the cable, but we don't have to analyze it as being part of our system. Okay, and you'll see what that means as we go on. We also have a pulley in our system. Okay, we will also consider this to be a frictionless, massless pulley. All right, we're trying to keep our analysis as simple as possible since this is a general physics course. In other physics courses and in more advanced physics courses, we would take those into consideration. But in this course, right, we're not going to do that. Okay? So our two objects would be this weight that's hanging and this mass that is this cart that is sitting up on the table. All right? The table itself would not be part of our system. All right? It would not be an object in our system. It's part of our system, but it would not be an object in our system. The car is resting on the table, but that's as far as it goes. Okay, let's look at the middle situation here. All right, we now have three objects. Okay, and they are connected by three ropes. Again, each one of these ropes or cables we're going to consider to be massless. All right, and so the blocks are connected by the ropes or cables, but that is all we need to be concerned about. And so they convey a force, right? Say this rope or cable here will convey a force between block A and block B, but that's all that it does. There is a tension in the cable, right, denoted by the letter T here, right? But that's it. We don't have to analyze it as one of the objects. We're not going to write a system of equations for the rope or cable, only for the blocks A, B, and C. All right? Again, the table, while it's part of our system, is not an object in our system. Okay, it's just the blocks. And as you do more problems, this becomes more obvious. Over on the right-hand side, we have what's called an Atwood machine. We have a mass hanging on a string or a cable over a pulley onto another mass over here. So what are the objects in our system? We have one object here. We have one object here. Our pulley is going to, again, be considered a massless, perfect pulley with no friction. And our cable or our rope here is going to be considered a perfect rope. There's no stretch, there's no mass. It is simply connecting the two objects together. So that's what a system of objects means. That's all it really means. Okay. All right, so moving right along, let's next talk about something called a free body diagram. There's nothing magical about a free body diagram. It just helps us in identifying the forces in our system. So in our system here, we have two masses. I'm going to call this one M1. We'll call this one M2. And they are connected by a massless rope over here. Okay? And M2 is also connected by another massless rope, and it is being pulled to the right by some force. So first, I'm going to say that there's a force due to a pull, and that is going to the right, all right, for object 2. And I'm getting a little bit ahead of myself. So let's take a look at object 2 first. All right, I want to identify all of the forces on object 2. Well, we've said that the forces that we need to be concerned with are gravity, pushes, pulls, and friction. Okay? Well, our blocks are on a frictionless surface. Okay? And you'll either be told whether the surface is frictionless or not frictionless. Okay? In this case, it's going to be frictionless, so we don't have any friction. Okay? But we do have gravity, and we do have pushes, and we do have pulls. Okay, actually we only have pulls in this case. Gravity is going to act on block number 2, and I'm going to label this the force due to gravity on block number 2. Okay. Remember the normal force that we talked about in the first lesson, right? And because our object is not accelerating in the y direction, it is simply sitting on the table, right, or moving along in the x direction on the table, but it's not accelerating at all in the y direction, we also have the normal force on block number 2. Right? And those are the only forces in the y direction. What forces do we have in the x direction on block number 2? Well, we have this cable over here, right, or this wire, or this rope, whatever you want to call it, is connected to block number 2. All right? We have the force of a pull on that rope to the right. The arrow here denotes that the pull is to the right. Remember that if you have a rope connected to something, a rope can only pull. A rope cannot push. And this should help you in analyzing the direction of forces or tensions when you're considering those forces for a particular block or object. Okay? So we've got our force due to our pull, the force due to gravity, the normal force, right? And what about this rope over here? Well, remember that a rope can only pull. That's what I just said. So what's the direction of the tension in that rope? What does it have to be? It's going to have to be to the left. Okay, because remember, a rope can only pull. If it was to the right, then that rope would have to be pushing, and that simply can't be the case. All right. So this rope is going to be pulled to the left. So there's going to be some tension T in this rope. Okay, and because our rope is a perfect rope, right, that tension T is going to be the same throughout the rope all along the length of this rope. We're going to have a tension T. All right, so that's all of the forces that are on block number 2. All right, let's look at block number M1 now. Well, we're going to have the force due to friction on that guy. I'm sorry, the force due to gravity on that guy. So I'm going to label that FG1. We're going to have the normal force. We'll call that FN1. And block M1 also has a rope attached to it. Ropes can only pull. All right? So it's going to have to be the force due to tension in that rope. It's going to have to be to the right as far as block M1 is concerned. All right? Remember, we're only interested in looking at block M1 at this point, not block M2. So as far as block M1 is concerned, that force has to be to the right. All right? We've now identified all of the forces in our system. All right? And this is one form of a free body diagram. I've simply labeled all of the forces in our system. All right? Does it have to be like this? No. Some people, what they'll do is they'll create a free body diagram and they'll replace the objects with dots. Okay? And we may draw our cables in with green lines here. All right? And we may label our forces like this. So it might be FG2 like this, FN1, FG1, whoops, FN1, all right, and we would have forces like this, all right, and this is the same as this diagram down below. It's really not any different. I've simply replaced the blocks with dots. It's a little bit smaller, a little more concise maybe. Either one of them is just fine as a free body diagram. Okay, so that's one example of how to draw a free body diagram. We're simply trying to identify all of the forces so that we can then take them and transfer them to Newton's second law. All right, so let's try another example. In this example, we have a pail hanging from a tree branch. Okay, so we want to identify all of the forces that are in our system. Okay, what's our system made up of? Well, our system in this case is simply made up of the pail, okay, the rope, right, and the tree branch. So this is our system. Okay, what are the objects in our system? Well, our rope is considered massless, all right, and so our object is really only the pail. We only have one object. All right. The tree branch itself is simply being used to hold on to the rope. Okay, so we're not really interested in the tree branch. That tree branch could have been a ceiling. It could be anything that could be holding the rope. And what we would like to know, all right, is we would like to know what all the forces are on our bucket. Okay. Well, what are the forces? Again, we have gravity. We have pushes, we have pulls, and we have friction. And we could also have a normal force. Right? Well, do we have gravity? Well, certainly we have gravity. And remember, the object we're interested in here is the bucket. Okay? Well, we have the force due to gravity on our bucket. Okay? And what other forces are on our bucket? Well, if we didn't have a rope attached to the bucket, our bucket would be falling. All right? So we have a rope attached, and remember that ropes can only pull. All right? And a pull is always going to be away from the object. So we have a force due to tension, and we'll usually just call that a T. All right? And that's about it. All right? There are no forces in the x dimension here. There are only forces in the y dimension. All right? So if I wanted to take this now, I've identified our forces, and I wanted to transfer these forces into Newton's second law equation. I have the sum of the forces in the y dimension are equal to the mass of the bucket times the acceleration of the bucket. Well, is our bucket accelerating? No, it's not moving. Right? It's motionless. It's hanging from the tree branch. So the acceleration in this case is going to be 0. So the sum of the forces in the y dimension equals 0. Now, what are those forces? Well, we have tension, all right? And the tension is positive because it's pointing upwards. So the sum of the forces in the y dimension, which equals 0, is equal to the tension minus the force due to gravity. Okay? So tension minus the force due to gravity in this case is equal to 0. What does that tell us about the tension and the force due to gravity? That they are equal in magnitude to each other. Okay? So this is why we draw the free body diagrams. We draw them so that we can identify all of our forces and easily transform them or transfer them over to Newton's second law. All right. So now that we've done our free body diagrams, let's do a couple of examples. So in our first example, we have a block that is lying on a frictionless table, so there's no friction between the block and the table. The block happens to have a mass of 25 kilograms, and I have not assigned any forces to it yet. We have 3 force vectors, as you can see, attached to the block, and they are, we'll consider those to be ropes. And let's say that the force vector pulling to the left is, say, 20 newtons, and the force vector pulling to the right, we'll say this one's 25 newtons, and this one is 40 newtons. Okay. We also have, so those are our forces in the x dimension. We of course also have the force due to gravity, and we have our normal force because this block is sitting on a surface. All right, so we will have the normal force. So now I've got my free body diagram. I can transfer these forces to our Newton's second law equations. Well, let's do the y equations first. The sum of the forces in the y dimension. Well, what are those going to be? Well, we have the normal force, all right, minus the force due to gravity, and that's going to equal 0. Now, I could assign numbers to this, right? I don't really know what the normal force is, but I can get the force due to gravity. Force due to gravity is equal to m times g. All right, and in this case, m is 25 kilograms. All right, and g is going to be 9.8 meters per second squared. All right, and I could come up with a number for our force due to gravity, and that would be 245 newtons. Now, notice I did not put a negative sign in front of the 9.8 meters per second squared. I didn't do that because we already incorporated the negative sign up here in our equation. Okay, if I had not done that, right, if I had simply put a positive sign in the equation up there, then I would have to incorporate the negative sign in the 9.8 meters per second squared. So make sure you don't double count a negative sign. Okay, so the force due to gravity is 245 newtons. Okay, what does that mean about our normal force? Well, it's also 245 newtons, except it's in the opposite direction. Now, does that give us much information? Not really. It just tells us a little bit about what the force due to gravity and the normal forces are on the block. Well, let's write the equation for the sum of the forces in the x direction. Well, what are those? Well, we have 20 newtons pointing to the left, So that's going to be negative 20 newtons, right? Because to the left is always taken as a negative sign. All right, and then we have the two vectors pointing to the right. They are both positive because they're pointing to the right. And then we have a 25 newtons, right, and a 40 Newton force. And that's going to be equal to, well, what's over on the right-hand side here? MA x in the x direction. So the mass is 25 kilograms, right, times A in the x direction. All right, well, let's add up some of our terms on the left-hand side. Negative 20 and 25 is 5. 5 and 40 is 45, so 45 newtons is equal to 25 kilograms times our acceleration in the x direction. All right, we divide each side by 25 kilograms, and the answer that we get for our acceleration in the x direction is a sub x is equal to 1.8 meters per second squared. So our block is going to accelerate to the right because 1.8 meters per second squared is positive, so it's going to be accelerating to the right, right, at 1.8 meters per second squared. Right? So that's how we take the forces from our free body diagram, we populate Newton's second law, and we simply solve the equation. Okay. All right, so let's do another problem where we have something going on in the y direction. Let's see if I can get this to slide down here. There we go. All right, so now we have a pail, right? And our pail is going to be pulled upwards. Okay, so it's accelerating in the upward direction, so our acceleration here is positive. All right, and we would like to know, say, what the tension is in the rope, all right, if we have some acceleration. So I'm just going to make up some numbers here. I'm going to say that our bucket has a mass of 20 kilograms, okay, and I'm going to say that our bucket is accelerating upwards at a rate of, say, 1.5 meters per second squared. Okay, so that's our acceleration. So this is what we know. So the first thing we want to do is we want to draw a free body diagram. Okay, and so we're going to do that. So what are the forces on our bucket? Our bucket is the main part of our system here. It's the only object in our system. The rope is in our system, the pulley is in our system, but the rope and the pulley are massless and they are perfect, so we don't have to consider them when we're considering forces on objects. Right? The only object is our bucket. Well, we've got the force due to gravity on our bucket, all right, and we have a rope attached to the bucket, which is pulling upwards, and so there's a tension T in our bucket. And ultimately what we want to know is we want to know what that tension T is if our bucket is accelerating upwards at 1.5 meters per second squared. Now the reason it's accelerating upward is someone is pulling on the rope from over here somewhere. So they're pulling and our rope is accelerating, our rope and bucket are accelerating upwards. All right, so we've drawn the two forces. There's only two forces. There are no x direction forces. There's only y direction forces. So at this point, we can write our equation in the y direction, right, for our forces. What have we got? Well, we've got T minus Fg, right? T is positive, Fg is negative because it's going in the downward direction, is equal to ma. Well, the mass of our bucket is 20 kilograms. Okay. And the acceleration of our bucket is 1.5 meters per second squared, and it's positive because it is going in the positive y direction. So positive 1.5 meters per second squared. Okay, so we have that. Now, we have one equation, we have two unknowns. However, can we calculate what Fg is? Certainly, we can do that. Fg here is going to be the mass times gravity. All right. Well, what's the mass? The mass is whoops, 20 kilograms times the acceleration due to gravity, 9.8 meters per second squared. All right, and again, I left out the negative sign there because we've already accounted for the negative sign right there. Okay, so that's why I've left it out there. So let's calculate what 20 times 9.8 is, and that happens to be 196 newtons. All right, so if I come over here, I can rewrite my equation, say T is equal to, T minus Fg, and Fg is 196 newtons, is equal to 20 times 1.5, right? 20 kilograms times 1.5 meters per second squared. So that is 30 kilogram meters per second squared. Okay, and a kilogram meter per second squared is also otherwise known as a Newton. Okay. All right, so what have I got? I've got one equation, I've got one unknown. And so what I want to do now is simply solve the equation. So if I add 196 newtons to each side, and I should have an N over here, all right, that's newtons. If I add 196 to each side, I get T is equal to 226 newtons. So that is the tension that exists in our cable. Okay, so what we've shown here is that we can have a system like a bucket that's being pulled upwards. All right, all we really need to do is identify the forces that are on our object, and again, in this case, we only had one object. Object is the bucket. All right, identify those forces. All right, write down all of the other information that we had, like the acceleration. All right, and then transfer everything over to Newton's laws, or Newton's second law. And then we solve the problem, solve the equation, we've got our answer. I hope that helps. For other examples, I've got quite a few other examples out on YouTube for Newton's second law. Take a look at those, and hope that those help you out.